See, everybody, when it comes to purification of organic compounds, just a minute. Yeah, we have various methods, out of which first one is crystallization method. Here, the process for formation of pure crystals of a compound by cooling the hot saturated solution of an impure sample of a compound in a suitable solvent, that is called as crystallization. What is the principle on which it works? Here, the solubility of solid in liquid increases as the temperature increases, and saturation solution at higher temperature, which on cooling crystallizes the substance. Or I can put the counter way that as the temperature is decreased, the solubility of the solid decreases in the liquid solution. Okay, that is the principle on which it runs. There are two types of crystallization forms. One is simple crystallization, the other one is fractional crystallization. When it comes to simple crystallization, okay, a solvent is selected in which the compound is sparingly soluble at a room temperature but appreciably soluble at high temperature, while the impurities are fairly soluble at room temperature. Okay, so impurities will get dissolved more, and the organic compound which we want to separate, that will dissolve less. So you can see solvent must have relatively low boiling point. These are for those cases where they are appreciably low boiling point, and it can be easy to be removed from the crystals. So it should be easy to be removed from the crystals. Okay. Now, commonly used solvents are water. Second, just a second. See. So a solvent must have relatively low boiling point so it can be easily crystallized. So commonly used solvents includes water, ethyl alcohol, benzene, acetic acid, ethyl acetate. These are very commonly used solvents. This solvent will dissolve the organic compound which we require, and rest of the uh, you know rest of the impurities will remain back. Okay, so that is typically how it is done. So I don't think this process requires a lot of explanation in terms of how the steps will take place. So it's pretty much self-explanatory. So I'm not getting too much details into that. Okay. Next, check out. Usually, in this case, the terms which are important are this. The hot filtrate after cooling separates the pure crystals, leaving behind the impurities in the residual solution called mother liquor. Okay. So mother liquor is that particular solvent form which also contains impurities. So keep that in mind. So what is mother liquor means? Okay. Next, colored impurities, if present in the sample, are removed by boiling the prepared solution of the sample with a small amount of activated charcoal before filtration. Okay. So again, it is just if you have any colored impurities, we use the charcoal. By charcoal, we can remove those impurities and make it colorless. And after that, again, we can use the crystallization process. See fractional crystallization. If a solid mixture has two or more valuable solids to be separated, then at different, obviously they have different solubilities, then we can use fractional crystallization. Okay. So fractional crystallization is simply just a method uh, at two different types, different crystallization temperatures. Got it? Next, check out sublimation. On heating, some solids change from solid to vapor state without passing through liquid state. Then that is called as sublimation. This is used when a solid mixture has sublimate organic substance and a non-volatile solid impurity. Okay, like camphor, naphthalene, anthracene, benzoic acid. These are typically used via sublimation. I mean, we can uh, these are all solid substances, correct? So there we can remove their impurities just by vaporizing them and condensing it back. Okay, that is how the sublimation is done. Check out distillation. Here, the process involves vaporization of an impure liquid at its boiling point and condensation of the vapors into pure liquid by cooling. This liquid is called distillate. The liquid begins to boil when the vapor pressure becomes equal to the external pressure, then the boiling point will occur. Here, there are two types, in fact, many types here. One of them is simple distillation. Simple distillation is a method employed when you have to separate a liquid from two liquids, in which there is an appreciable boiling point difference, that is around 30 degrees. If you have around 30 degrees. So you can see that here is the impure liquid and we heat it strongly till the boiling point comes. One of the vapors will start traveling through this one. And here this is a condenser. So it will condense this vapors into liquid. So this is the distillate, pure liquid which you will get, that is a distillate. Okay. And the residue which is present will be of the other liquid. Okay. Fractional distillation. This method is used when a mixture contains two or more valuable liquids and boiling point do not have a significant difference. That means it is somewhere between 1 to 15 degrees. A very small amount of boiling point difference is there. Then we'll go for fractional distillation. Okay. Typically, this is how the fractional distillation will look like. Correct. Fractional distillation will have various columns here. You can see these are called fractionating columns. Okay. In one column, if at all, just like how I put this output here, imagine the same output, I'll put it here. I'll put the same output here. Now, between these two, suppose I have a methanol and an acetone. Methanol boils at 65 degrees. Acetone boils at 56 degrees. Okay. In that case, you would notice acetone, which has lower boiling point, will be appearing in the first distillating column, and that you will condense here and convert into distillate. And you keep on boiling till the next column here. Here again, you make a similar kind of connection here, and anything which is coming at relatively lower distillating column, that will be having higher boiling. So that's how we can remove out the methanol form. Okay. Crude oil, for example, crude oil can be heated between 700 to 1200 degrees. Sorry, this is 1200 degrees. 70 degrees to 1200 degrees. So if you heat it that strongly, you will notice that first you will, the first elements which you'll get here is liquid petroleum gas and CNG. Okay, CNG, LPG. These are the ones which you will get here, which will have methane, butane, and all these compositions. Then we'll get, distillation, slightly lower distillates, you will get petrol. Further, if you go after certain distillation columns, you'll get diesel. After that, you'll get naphtha. Then you'll get, wax. Then lastly, you will have fatty acids and all. Okay, that's how the separation is being done using fractional distillation. Okay. So mixture is heated at high temperature, pass through a condenser, and as the vapor condenses, they'll partly on the glass beads and fall down. As the condensed vapor falls on the hollow glass beads, they again vaporize and ascend. This leads to the infinite number of vapor condensation processes, giving an equilibrium in the column. So the components with the lowest boiling point comes out of the condenser first and followed by the rest. Crude oil, methyl alcohol acetone separation, benzene toluene separation. These can be done using fractional distillation, right? Next one is a distillation under reduced pressure. Distillation under reduced pressure typically is done for compounds having very high boiling point, like glycol, glycerol. These are the forms. Glycerol has extremely high boiling point of 290 degrees. Okay. So it becomes very difficult to handle such type of temperature with these glass tubes. Got it? So what we do, we will make sure that this entire flask which is present, right, is being airtight first and remove as much vapors as possible here and try to keep it at very, very low pressure. So now this entire thing is at a very low pressure. So when it is at a low pressure, and then you take this oil bath and start heating this glass in which we have the substance, right, which we have to separate out, like glycerol and all. Okay. Then we will pass hot air if required, and then start burning around it, and you will see vapors will start coming out of it, which will be again using Levick condenser. We will condense everything here, and this is going to form a distillate. Okay. Like you can see that here there is a vacuum pump just to ensure that here it will get easily uh, you know evaporated, so these vapors will come more easily here. So then, as in when you start decreasing temperature, it will start getting distillated. Okay. So this is a typical setup. Remember, glycerol, glycol, anything which is having more number of OH, any carbohydrates, amino acids, if you want to separate, best method is distillation under reduced pressure, or also known as vacuum distillation. It is one and the same, vacuum distillation or distillation under reduced pressure. Okay. You can see employed for liquids which decompose at or below their normal boiling point. Boiling point of the liquid decreases with the decrease in the external pressure. So glycerol, which normal boiling point is 290, now we are distilling that at 180 degrees under reduced pressure of 12 mm. So you are only, instead of keeping 76 mm of mercury, which is atmospheric pressure, now you are keeping a pressure of just 12 mm. So the boiling point reduces to 180 degrees. Okay. Esters can also be separated by this method. So glycerol and esters are the examples for vacuum distillation. Next, steam distillation. See, here it works on the principle where, one of the organic compound is immiscible in water. It should be immiscible in water. So suppose if I have an organic liquid, and then the sum of the vapor pressure of one liquid which we want to separate out, that and the vapor pressure of water together, okay, P1 plus P2, that is partial pressure of the one which we are separating out plus partial pressure of the water. If both of them becomes equal to atmospheric pressure, so that is this must be equal to atmospheric pressure. So when this total pressure becomes equal to atmospheric pressure, then the evaporation will start. Okay. So steam will take the vapors of that organic compound and start coming out. Okay. So that is passed through a hot liquid mixture. So steam liquid boils at low temperature, then its boiling point. For example, I'll show you one example. Aniline is purified by non-volatile liquid impurities by steam distillation at 98.5 degrees. See, otherwise, vapor pressure of aniline, right? Sorry, the vapor pressure of aniline, if you notice, is just 43, and vapor pressure of water is 770. Okay. So when these two together will come to be 760, then that evaporation will start happening. Okay. And you see that boiling point normally of aniline is around 98.5. So therefore we use this. So you can see the steam here, which has been sent into the container. Sorry, this is water, steam generator. So the steam goes into this, liquid impure organic compound. From there, the steam will take along with the vapors of the compound and start getting condensed. So one important criteria in this is that the water and the distillate liquid which you have, both should be immiscible so that we can separate out easily. So you might see that aniline is stored at the bottom, water is coming on the top, and they are immiscible, so separation becomes easier. Okay. So two important conditions, students. One is for steam distillation, the liquid should be immiscible with steam with water. Correct. Second, it should have more solubility in vapor state compared to liquid state. Okay. So it should dissolve more in the steam compared to that of water. You can see the steam mixture is cooled to get a liquid which has a two layers. Further, they can be separated by simple filtration. Orthonitrophenol can be separated by paranitrophenol using this. So wherever you have ortho and para cases, right, they all can be extracted via this steam distillation. Next, differential extraction. See, this method is based on solubility of organic compounds in organic solvents. Okay. So organic compounds from an impure mixture is recovered by treating with mixture with organic solvent, which is dissolve the compound here. So you can see first you have this mixture here. Then I'm adding an organic solvent on top. So what happens? From that mixture, it will slowly start dissolving in that organic solvent. Okay. After that, this aqueous layer is separated, organic layer will remain, and the compound present in the organic layer is later separated out. This is called differential extraction. Okay. Next, you can see benzoic acid can be removed. Benzoic acid can be recovered from the aqueous solution containing benzoic acid and NaCl by treating it with benzene. So when you add it to benzene, benzoic acid will mix with the benzene, right? And that will become an organic layer. NaCl will mix with H2O, that will become aqueous layer. So that's how they both can be separated. Next, the next technology used is chromatography. Chroma as in color. So this is the most efficient technique, and most of the research laboratories use this to separate any compounds and then purify it. Separation based on the differences in the affinity of the compounds of mixture to two different immiscible phases. So we divide here in terms of phases. Okay, one phase is called stationary phase, the other one is called mobile phase. In stationary phase, you will see only liquids and solids. In mobile phase, you will see liquids or gases. Okay. Check this. Partition between the two phases is mainly due to difference in physical properties like adsorption or difference in solubility. Okay. If the difference is due to adsorption, then we use adsorption chromatography. If the difference in the phases is due to solubility, then we'll use partition chromatography. So we will convert this into two types of chromatographies. One is adsorption chromatography, the other one is partition chromatography. Notice this area as a straight questions are asked earlier, like which phase belongs to what, okay? Which type of chromatography belongs to what type of category. Check. Stationary phase if it is solid, and mobile phase if it is liquid or gas, then it is adsorption chromatography. Okay. Within adsorption chromatography, we have two kinds: gas solid chromatography, liquid solid chromatography. Next, see, this liquid type of liquid solid chromatography can be again converted into, I mean, divided into liquid column chromatography or thin layer chromatography, TLC. So remember, TLC, thin layer chromatography, belong to adsorption chromatography. Okay. While partition chromatography, stationary phase is liquid, mobile phase is liquid or gas. And this time it will be liquid chromatography and gas liquid chromatography. Okay. Now, notice what is happening in column chromatography. A column of adsorbent silica gel or aluminum gel is prepared by suspending finely divided powdered adsorbent in a suitable medium like petrol or something. Okay, petrol or ether. Now, the mixture to be separated is dissolved in the solvent and loaded into the column as the solution descent into the column. See, this is how it is. So first we have loaded with all the adsorbents here. These are all the adsorbents. Like pebbles, small pebbles we will have. Then we will add, uh, our mixture here, ABC is a mixture added. Then we added some sand. On top of that, we are adding a mobile phase. Okay, we will add a mobile phase. Mobile phase is the one which will take this ABC and start moving down the column. Okay, and the mobile phase movement of the solvent is called as eluent. It is called an eluent. So eluent will start moving in the adsorption column by taking ABC. So what would happen? Suppose if you notice B and C are making more movement as compared to that of A. B and C are making more movement as compared to that of A here. Okay, just a minute. You can notice A and B and C started separating out in the adsorbent. Okay. This is to do with the nature of adsorption. Out of A, B, C, possibly A is trying to adsorb more compared to B and C. And as you start moving down here, slowly you will see B is also getting relatively more adsorbed than C. Okay. So eventually, as it starts traveling down, you will have a solution containing mostly C here. Okay. Because C is less adsorbed. Then after some time, you will get B here. Here. And after some time, you will get A here. So that's how you are able to separate it using adsorption chromatography. Clear, everybody? Now, like I said, thin layer chromatography is also an adsorption chromatography. Now, in a thin layer chromatography, what we do, suppose if at all I have to separate two substances, here we will take this glass plate. This is for a small samples to separate out, okay, that have a thickness of around 0.2 mm thick of a slurry of adsorbent is applied on the glass plate. So this yellow color which is I'm showing, this is all adsorbent, stationary phase which we have kept, okay, on a glass plate or a celluloid paper. It is dried and the solution of mixture whose components are to be separated is applied here as a dot, as a small spot it has been applied. And it is applied just 2 centimeters above the end of the TLC plate. Okay. And after doing that, you will see what would happen. As you provide a solvent which will act like a mobile phase, that will start slowly going up. Okay, that mobile phase will start moving up here. And the solvent will start moving up. This solvent is called as eluent. Okay. It will go and reach up to the distance x, let's say. From this spot onwards, from the spot distance, the solvent is maximum going up to x. And this dot is only going up to y distance. This is up to y distance. Done. So you will show, you will see that x and y is the distance which they have traveled. X is traveled by solvent. Y is traveled by the spot. Okay. While it is traveling, one component will travel up to the spot A, I mean this spot, and one component will travel up to this spot, which is y distance here. This is y dash, y and y dash. Okay. Now, this is called a term is been defined known as retention factor. So the retention factor is equal to y dash upon x, which is chromatography. Sorry, x is the distance traveled by the solvent. So y dash divided by x and y divided by x. These are called the retention factors for compound A and compound B. That is the distance traveled by the compound from the origin by distance traveled by the solvent. Okay. And generally, RF value will always be lesser than 1. Okay. So whenever it is column chromatography, it can be sampled using the thin chromatography and Observe how much is the retention factor for this. Now notice the plate is then placed vertically. I mean, I have explained you that solvent has the highest rate of the travel leading to the edge of the solvent. And this is called solvent front. Spots A and B are visible if they are colored. Spots are colorless if they are detected by putting plate under UV light. Now notice if a compound absorbs ammonium iodine, they show up brown color spots generally. Amino acids form colored with ninhydrin. Okay. So as ninhydrin will start moving around as a solvent here, as soon as it touches the amino acids, it will start giving a color. Okay. Next, let us see what is paper chromatography. Liquid partition chromatography. Here, liquid partition chromat. This is to do with the solubility. A strip of chromatography paper is taken. It contains water trapped in it at a molecular level, which acts like a stationary phase. Okay. It is based on the fact that different components of the mixture undergoes partitioning between the water and organic solvent to different extents. Okay. So you can see, ensure that the edge of the strip dips in the solvent, but the spot remains on the surface. Just like how we have done it for the thin layer chromatography, same way, this is a paper now. That paper already has a liquid on surface of it, which is strongly held onto the paper. And then we are taking a sample here, and through that, it will have an extension. So as it starts moving, it will go up to this, which is um, the amount of distance traveled by the solvent. Then this is the amount of distance traveled by solvent, and this is the amount distance traveled by the solvent B. Clear on that, everybody? This is called paper chromatography. And everyone, right? So this is about paper chromatography. Okay. So mainly, guys, you need to understand this difference. That's it. So the main part of this chromatography is this one, which belongs to what category. That's it. And very rarely that has been asked to identify the retention factor. These values will be given. You just need to know how to calculate the RF value. That's it. Clear on that? Clear? Right. One second.